will describe section 4.3, fundamental polynomial operations. A polynomial in X is the sum of a finite number of terms of the form a times x raised to the nth power, where a is any real number and n is a whole number. For example, 5x squared plus x minus 3, or 1.2 times c to the third power plus 5 plus 1, 5.1. A multivariable polynomial is a polynomial with more than one variable. For example, in the examples below, we have the variables y, z, and w on the left, and on the right, a, b, and also ab. So we have more than one variable. Degrees of polynomials. The degree of a term is the sum of the exponents of all of the variables in the term. So in this first case, we have one variable, x. That x is raised to the second power. Since it is the only one, we would say the degree of this term is 2. In this case, we have one variable raised to the third power. It is the highest term, so the degree of this term would be 3. The degree of a polynomial is the highest degree of all of the terms in the polynomial. So in this case, we have 3 separate terms. In the first term, we have a variable raised to the third power and a variable raised to the fifth power. Since this is one term, we would add those exponents together, even though the variable y and z are not the same alphabetical number, or variable alphabetical y and z are not the same letters in the alphabet. We would still add them together to get our degree since this is combined. So we would add 3 plus 5 to get 8, and we would say this polynomial has a degree of 8. And the last example down here, the highest degree of all the terms is 3. Our others have a 2 or a 1 plus a 1, which is 2. So the highest degree of our polynomial here would be a degree of 3. So a monomial has just one term. Even though, again, c and d are different variables and we're multiplying them together, this whole thing is being multiplied together, and so we call it a term. So this is a one term, a is one term, and 5x squared is one term. So these are all 3 separate examples of a monomial. A binomial has 2 parts, so we are either adding or subtracting pieces together, and there are 2 separate parts. The 3 is separate from the 5x squared. The negative 4 is separate from AB, and our 2 is separate from C. A trinomial has 3 terms, so our first term is 5x squared, the second term is x, and the third term is negative 3. In the second example, a times b is the first term, negative a is the second term, and positive b is the third term. And then our third example, negative c squared is the first term, c is the second, and 2 is our third, so trinomial. So in these cases, we can state the degree of the polynomial and whether it is a monomial, a binomial, or a trinomial. So all of these are polynomials, we just have to say which type. So in our first example, we would have m is raised to the first power, n to the fourth. 1 plus 4 gives us a degree of 5. This is all one term. It's all being multiplied together, so that is a monomial, one term. In this case, we have a 5 exponent plus a 2 exponent, which gives us 7. On the right, we have a 3 plus a 1, which is 4. So the larger of those 2 is 7. So this is a degree of 7. And we are adding 1, 2, 3 terms together. So triangle has 3 sides. This has 3 terms, so this is called a trinomial. And in our third example, we have an exponent of 1 plus 2, which gives us 3, versus an exponent of 1. The higher of those is a 3, so it's a degree of 3. And we are subtracting 2 separate terms, 2 meaning or a bicycle has 2 tires, binomial. So we can use these polynomials and we can add them together. So if we're adding polynomials together, we first want to list these in decreasing order and also combine our like terms together so that we can simplify. So first we'd have 5x squared minus x plus 6 plus 2x squared minus 3. So if I'm looking for like terms, the x squares are a like term, x is a like term, and our whole numbers are like terms. Excuse me. So in this next section, we're going to combine those. So we would say 5x squared, this is a positive, plus 2x squared. Let's combine our x's. We have just one, so negative x. We can add that next. And then let's combine our whole numbers. 6 is positive, plus a negative 3, which is still negative. So if we add these together, 5x plus 2x gives us 7x squared minus x. 6 minus 3 is positive 3. And then we can, 7x squared plus a negative x would be the same as saying 7x squared minus x plus 3. And this is written in decreasing order because we have our x squared, our x to the power of 2 is first, x to the power of 1 is second, and our third is a value that does not have an exponent. Here's another example. So we can combine our like terms and we can put them in decreasing order. So our highest variable is an x squared. We can put that first. We can do adding fractions. We have to have the same denominator. So the least common multiple between 2 and 5 is 10. So I can rewrite 1/2 as 5/10 and 1/5 as 2/10 x squared, plus we had our 6x, negative 6x, and a negative 2x, which would equal negative 8x, and then plus our values without variables would be that 1/3 that's positive minus 1/2, and if we have a least common multiple between 3 and 2 would be 6, so 1/3 is the same as 2/6, and 1/2 is the same as 3/6, and if we subtract 2/6 from 2/6 minus 3/6, we'd be left with negative 1/6. So our final answer is 7/10 x squared minus 8x minus 1/6. Here is another example where we're adding and we want to look at common exponents and put them together. So the first exponent here is x to the third power. We'll combine that with negative 3.4x to the third power. Next, we can combine our x squares. So we have negative 5.6x squared minus 1.2x squared plus 4.5x is the only one that has just x to the first power plus a positive 5 minus 7. And then we can combine those. 1.2 minus 3.4 equals negative 2.2x cubed. Negative 5.6 minus 1.2 equals negative 6.8x squared. Nothing happened to the 4.5x since it was the only one, and 5 minus 7 equals negative 2. We cannot simplify this any further because all of these variables are raised to a different power, so they're not the same. We can also subtract two polynomials, change the sign of each term in the second polynomial, and then add like terms. Here is an example. So if we're subtracting, what we're going to do is distribute that subtraction sign to every value inside the parentheses here. So I would have negative 2a to the fourth power, negative 2a, and the subtracting a negative 3 would make that plus 3. And then I'm able to add all of these like terms together and group them in the same way based on exponents, put all the a to the fourths together, a's together, and whole values together to simplify and get a to the fourth plus 3a minus 3. Sometimes polynomials are used to predict values. In such cases, we can evaluate the polynomial. We do this by substituting a known value for the variable and determining the value of the polynomial. So here's an example. Town planners believe that the population of Bradenton can be estimated by the polynomial 0.5x squared plus 65x plus 25,750, where x is the number of years since 1985. Use this polynomial to estimate the population of the town in 2000, 2015. Round your answer to the nearest whole person. So 2000 is 2000 minus 1985, which is 15 years. Because we're looking at x as the number of years since 1985. So we would replace that x in this equation with 15 for the first part, because we're finding since 2000. So we can say 0.5 times 15 squared plus 65 times 15 plus 28,750 would give us approximately 29,838 people. We did the same thing to find how many since 2015. Well, that would give us a difference of 30 years. So if x equals 30, and we substitute that in, we would get 31,150 people. And that concludes this section, 4.3.